Just like that last lesson, our learning objective here is to discuss nutrient loss and tile drainage, but now we're focused on phosphorus rather than nitrogen. The primary way phosphorus moves in the environment is via surface runoff and erosion of soil particles to which phosphorus is bound. That's particulate phosphorus. Now we've talked about some of this before, but for example, when you see situations like this is a sediment and phosphorus problem associated with surface runoff. This is not a nitrogen problem in general, this type of surface runoff and erosion. Again, we've covered some of these concepts during the week when we talked about the phosphorus cycle, but as recap, total phosphorus is comprised of both particulate phosphorus and dissolved phosphorus, and the dissolved form is actually more biologically available than the particulate form of phosphorus, which can immediately lead to eutrophication. That dissolved form can immediately lead to eutrophication. And side note, remember, there is no gaseous phase of phosphorus, so we're not concerned about gaseous losses of phosphorus. This is very different than nitrogen. Forms of phosphorus present in surface runoff or subsurface drainage will depend on the soil type, historical applications of phosphorus and the soil test phosphorus level, land use, and associated land management practices. The soil itself has a high capacity to hold or absorb phosphorus, but overloading the soil with phosphorus, either with manure applications or fertilizer applications, is one of the most important ways that phosphorus can be lost to water. Overloading the soil is one of the most important ways that we lose phosphorus from agricultural systems. For subsurface drainage in particular, the ability of the soil, a given soil, to leach phosphorus to drainage pipes, subsurface drainage pipes, depends on biogeochemical processes in the soils. Things like adsorption, desorption, precipitation or dissolution of phosphorus in the soil, and mineralization of organic forms of phosphorus. And those are processes that are happening in the soil. To cause an environmental problem or concern, there's two things that need to happen together with phosphorus. There has to be a high source of phosphorus, that is a soil that has a very high soil test phosphorus level, or great over applications of manure to a system. And that high source of P has to be overlapped with a high transport factor. Problems occur when these two factors come together. This is called a critical source area, and management of phosphorus and mitigation practices for minimizing phosphorus loss should focus on areas where these two conditions intersect. These are called, again, critical source areas. A high phosphorus source with little opportunity for transport might not constitute an environmental threat. Likewise, a situation where there's a high potential for transport, like a lot of runoff is going to happen, a very steep slope that doesn't have any sort of conservation, tillage, or conservation practice, that might not actually be a concern if there's not high phosphorus in the soil. So you have to have the high P source and the high transport factor to really have a critical source area where we should be focusing our attention with phosphorus and water quality. In terms of agricultural management, critical source areas include areas that have legacy phosphorus. Oftentimes, this isn't the only case, but areas of legacy phosphorus result as a result of buildup of phosphorus in the soil, especially beyond crop needs. So legacy phosphorus results in buildup of soil P beyond crop needs. Legacy phosphorus sources can also be found in riverbanks and stream banks, lakes, reservoirs, wetlands, anywhere where phosphorus, especially particulate phosphorus, has settled out over time. And the contribution of legacy sources, for example, in lakes or reservoirs or stream banks, contribution of that legacy P on a watershed scale is not insignificant. That legacy P that's washing out of stream banks or out of reservoirs can be a very significant part of phosphorus balance across a watershed, especially if that phosphorus has been accumulating in those natural bodies for many years. This legacy P can be remobilized or recycled, acting as a continuous source of phosphorus to downstream bodies for years, decades, even centuries. Now here's a nice illustration from Dr. Sharpley, Dr. Andrew Sharpley, and others that nicely illustrates the concept of lag time involved between doing a conservation practice and actually seeing an improvement in water quality. There's a lot of great temporal effects illustrated here. This is especially important for issues of legacy phosphorus in fields. For example, if you have legacy phosphorus in your field here, there will be a slow release of phosphorus from the field for years, decades, even centuries potentially. And then we have uptake and release of phosphorus by streams and banks and sediments. And then at the end, there's time for a water body to biologically respond to an increased P input or also to a decreased P input. So there's time for the water body, time required for the water body itself to respond to any changes in water quality. I also like this illustration because it shows some of the social side to conservation practice adoption. For example, it takes time for farmers and landowners to adopt conservation practices, and then it can also take time for certain conservation practices to really become effective. And so there's social factors, there's system response factors, there's hydrochemical response factors, and this illustration does a nice job showing all of those. Again, I'm talking about the complexity of agricultural systems and natural systems, some of the challenges that that complexity presents in terms of improving water quality. Here's another lag time graph. This was created by the Council on Agricultural Science and Technology many years ago, so it's an old figure, but one of the best I've seen illustrating lag time from adoption of conservation practice to actual water quality improvement. WQ is water quality improvement. For example, for nitrate, I'm looking at the median bar here. It could be 10 years between when you do a nitrate water quality practice, you put that on your farm, 10 years until you actually see a water quality improvement. This of course depends on a lot of factors like where do you expect to see the water quality improvement? Is it in a local lake or is it all the way down in the Gulf of Mexico? But you can see for phosphorus, this lag time could be, anywhere from 10 years to maybe about 50 years. Note that x-axis is a log scale on this figure. So our challenges are cut out for us in terms of improving water quality. So what are the normal quote-unquote concentration ranges for phosphorus in drainage water? On the left, I'm showing the dissolved phosphorus concentration across literature when I did this survey of literature several years ago. And on the right graph, the left graph is dissolved phosphorus, the right graph is total phosphorus. These are concentrations. And it makes sense that this total phosphorus bar would be higher in general than the dissolved phosphorus bar because dissolved P only makes up a portion of total P. Our median for dissolved P is about 0.021 milligrams per liter. Our median for total P is 0.31 milligrams total P per liter. Now we'll go back to the US EPA ecoregional nutrient criteria. You'll recall that we are in this orange region here, region 6, which is the Corn Belt. So coming to our criteria, we'll just look at lakes and reservoirs. Ecoregion 6, our ecoregional criteria for total phosphorus is in milligrams per liter, 0.0375. You'll remember the median from that last slide was 0.31 milligrams total phosphorus per liter. That's 10 times higher than the concentration here in the recommended criteria. Well, it can also talk about the Illinois nutrient criteria, which was developed as a result of our nutrient loss reduction strategy process. And in milligrams per liter here, rather than micrograms per liter, our total phosphorus criteria are around 0.11. So our median value across that survey of literature for total phosphorus concentrations was again 3 times higher than the recommended criteria here in Illinois. One last note about phosphorus criteria, there is no phosphorus maximum contaminant level for drinking water. Excess phosphorus in our bodies is typically readily excreted and does not pose a health risk. So there is no phosphorus drinking water criteria. There is no phosphorus NCL. Moving from concentrations to losses of P, here are losses of P in drainage water across literature. less than 1 in general. Less than 1 kilogram phosphorus lost per hectare, those are metric units, kilogram phosphorus lost per hectare for either dissolved phosphorus or total phosphorus. Very small loads or losses of P coming from through tile drainage systems. So here's the real kicker for this lesson. Phosphorus loss from agriculture is generally not of economic importance to landowners or farmers because it's such a small percentage of the phosphorus that would be applied. It's generally agronomically inconsequential. However, because phosphorus is naturally present in such low amounts in freshwater in particular, even adding a very little bit of phosphorus can lead to algae blooms. And that's why the phosphorus criteria concentrations that we just talked about are so low. And they're usually presented in micrograms per liter because they're so low. I'll also remind you that in freshwater, cyanobacteria, which is blue-green algae, which can be very toxic when we have blooms of blue-green algae, cyanobacteria are able to fix their own nitrogen from the atmosphere. They're nitrogen fixers. And so that's why phosphorus is limiting for their growth. When you add a little bit of phosphorus, these cyanobacteria don't need nitrogen because they fix it themselves. So adding a little bit of phosphorus can lead to situations like you see here, cyanobacteria, blue-green algae blooms. So to reiterate, very small amounts of phosphorus leaving fields, either in surface runoff or subsurface drainage, can cause important negative environmental effects. This disconnect between phosphorus in terms of agronomic rates and the very, very small concentrations that can lead to eutrophication of surface waters is one of the largest challenges of managing phosphorus in the environment. With that, see you next week.